All right, thanks everyone. I'll kick it off and then hand it to Kurt here. So I'm from Nevados. My name is Jenya. We're a tracker company. We really focus on trackers that can operate on any topography, really any topography, but what the challenges that come from that is modeling. Kurt used to be with Nevados. He's now at Terabase and has developed some of the underlying methodologies at Nevados to perform the novel tracking schedules to avoid any row-to-row shading for any topography. And with that, I will get out of the way and hand it to the person that actually did all the work. I just am still at Nevados.
Thanks, Jenya. I like to start my talks off with lots of caveats, I think you've noticed. Obviously, I'm no longer with Nevados. A lot of this work was done about a year ago. And I have the worst memory out of anybody I know. So some of you might have questions and I might not remember what I actually did. I also want to caveat that this isn't a performance model. This isn't a full end-to-end. This is just a few steps we took in a direction to sort of see what the effects might be. Okay, so first off, if you are not familiar with the Nevados tracker, Nevados has maybe an unfamiliar geometry. Basically, if you look at this photo, you can see that there are basically bearing gaps at every single pile. And at each one of those bearing gaps, the tracker geometry can change, as in the torque tube angle can change. And that's how the Nevados trackers follows terrain at such a high degree. Here's an infographic that shows you different types of bearing that they can place on different types of piles, and how each different type of bearing can allow more or less torque tube deflection. Okay, so most of my work at Nevados was developing TRACE, which stands for Tracker Rotation Angle Computation Engine. It's not a ray tracing platform, so sorry for that naming, my bad. It's more of a ray casting engine. So we don't compute the shadow ray, we don't compute the bounce ray, we just do one ray cast. That's our ray cast. Basically, we can do this across every single bay, testing across a bunch of different geometries and figure out which angle reduces shading to nothing. Trace isn't really the topic of this talk, so I'm going to skip over it. If you have any questions, please just come and talk to me. I also want to talk about terrain modeling in general, is in like, just like last talk where I was talking about how diffuse irradiance optimization is sort of tracker specific. At this point, terrain aware is also tracker specific. Different tracker companies will do different things. Different tracker companies have different time steps at which they send commands. Some tracker companies will control groups. Nevados in particular will control the individual tracker. Another thing, sorry, is that our terrain-aware backtracking strategy, we're not claiming that it's the global maximum. If you think about the sort of combinatorics of you have one tracker here, this one can be at one angle, this can be at some other angle, or another angle, or another angle, and you compare all of the different possible relationships of different tracker angles, it becomes quite a wide number of permutations you can possibly have in terms of all the angles your trackers can have at your site. And so what we're saying is we have found some local maximum that hopefully gives you a better performance than if you just chose your standard ground coverage ratio based backtracking strategy. Okay, so what we did is we took an example site. We have some contour lines here. This is basically a site that faces towards the northeast. And so just like Laura mentioned, if you have a site aspect in the northerly direction, you're going to have some amount of loss associated with that. Of course, thank you to PVLib, none of this would be possible without them both in terms of guidance, in terms of talking to them about the problem, and in terms of the implementation of software features. So what was not studied, this is not a performance model. This is not comparing to actual energy. This is a desktop simulation. We're mostly interested in the irradiance or effective irradiance. So no electrical mismatch, no tracker self-shading, and we use the Perez model. Okay, so first off, we want to know what happens when you just use your terrain-naive standard GCR-based backtracking strategy. Obviously, there's tools now that can do this for you in terms of the energy model, just like the PV case presentation that just happened. But basically what we did is we simulated the POAI for every single bay. And so for a Nevados tracker, you might have one tracker with 11 bays. Each one of those bays has a different angle that it's facing. Okay, so we calculated that. And then basically we ran our Rhee casting calculation to figure out if there was any shade. We assumed 100% shading electrical effect. So if there was any shade on the module, we reduced the direct irradiance portion to 0. And then we took basically a weighted average of that effective POAI and no consideration of diffuse shading. And then what we did is we ran our trace engine, figured out which angles would reduce the amount of shading, and then ran the same calculation. What we saw at this site's in Illinois, I believe, is the Nevados backtracking performs better than the GCR-based backtracking, which I think is hopefully not too surprising. So there's another thing that you can possibly do to improve your terrain-aware backtracking. Instead of controlling every single individual tracker separately, what you could do is you could change the set point of your GCR-based algorithm. So even if you physically set your trackers into the ground at, let's say, 35% GCR, you can tell the backtracking algorithm that you're at 40%, and so that your tracking algorithm will backtrack your trackers more aggressively and reduce the amount of shade. So we were curious of like, how does that perform? So basically we did the same thing. We just tried a bunch of different ground coverage ratio for the algorithm set point. And you can see that as you go from the site-specific 36% GCR, you get up to 42%, you're reducing the amount of shade, and then eventually your angle of incidence gets worse and worse. And so there's some local maximum there. And that's the local maximum for this site that we found. Obviously, different sites, different locations, different terrain is going to affect what you get. I kind of like to think of this terrain problem as like a problem of finding bookmark or bookends. So I think of like the best you could possibly do is if you graded your site entirely flat. That's using your standard GCR. There's no shading, rotor shading. And then the worst you can do is just use your standard GCR-based backtracking. And for this site in particular, the Nevados backtracking was able to recover 63% of your best case scenario to your worst case scenario. So how would you do this in PVSys? There's a couple constraints in PVSys. PVSys will calculate your tracker rotation angles for you, and then PVSys will use Rhee for the retro transposition model. And so basically what we did is we started with the terrain-aware POAI calculated from PVlib, the weighted average across all of the thousands and thousands of bays. We retro-transposed using GTI Durin. So now we have the horizontal components. We created a custom MET file and uploaded those horizontal components. And now PVSys can transpose, if you use the standard tracking angles, to the transposed irradiance that we want it to. That's probably a little bit complicated, and if you want to know more, just come talk to me afterwards. And then got to shout out Plan Predict, of course. In Plan Predict, you can put in custom tracker time series. And so basically, it's a little bit easier. You can just average all of the angles that the trackers went to. And then you can see that you get a pretty similar result to if you did the weighted average retro-transpose. And that's it. Thank you.
Tough.